Now, Dr. Benjamin Hatton, Associate Professor and Associate Chair of Material Science at the University of Toronto, will talk with us about smart materials for building surfaces. Dr. Hatton, you can speak now, and we apologize for making you wait so long.
Okay, no problem. Can you hear me okay?
Yeah, yeah, sound is clear.
Good. Okay. Um, well, thanks very much for inviting me to this meeting. I'm going to share my slides now. Okay, hopefully you can see that okay. Is that visible for everyone?
Yes.
Yeah, good. Okay. Well, I'll be speaking today about kind of a different topic, I think, from some of the metallurgy that we've heard about. Although metallurgy is kind of my background in my undergraduate studies, but these days I kind of work on smart materials. And so this project today I'll be speaking about is an example of smart materials for building surfaces, building facades. And this is a collaboration with a researcher in the Department of Architecture. My research I'm on the second slide now, if it's working okay. And my research generally is about surfaces, surface properties, and engineering material surfaces. So we look at porous structures and surface topographies, wettability of surfaces, adhesion. A lot of my research now is also on bacteria growing on surfaces. But we also have this part of my group working on smart materials and smart surfaces. So we're interested in these kind of designs that have large fluidic networks. And well, the problem that we're talking about here in this project is about buildings and the energy consumption of buildings. In fact, buildings, generally speaking, consume the largest amount of energy globally. So if you consider heating energy, cooling energy, lighting energy, it's about 40% of the total energy in the globe in most countries used for buildings. In the United States, it's about 75% of the total electricity. What we're interested in is that buildings are generally static in their properties. So the materials at the building facades, the surfaces, are static materials. They're not changing their properties to adjust for different solar conditions or seasonal conditions, like the optical properties. And so there's obviously been some recommendations, new kind of materials that improve insulation and heat conduction, energy efficiency. But again, most of these materials are static materials. And one of the big problems in modern material design, modern building design, is the use of glass. A lot of modern condominium buildings, office buildings are glass facades, which is good for light control, a lot of light in daylighting from solar lighting, but the problems of energy efficiency are from solar heat gains and thermal insulation losses. So glass is not a good material from an energy efficiency point of view. And of course, the amount of air conditioning and the energy for air conditioning in the globe is increasing a great deal. So especially in a warming climate and the problems of solar, so comfort, interior of buildings means that the amount of air conditioning is increasing. It's increased about 3 times in the last 30 years. It's predicted to increase again in the next 30 years or so, especially in some parts of the world that are getting very hot, that have increasing ability to purchase more air conditioners. So this is a problem. We have a lot of energy and requirement for air conditioning in a warming globe. Coming back to windows then, we're suggesting, and other people, that windows really should be dynamic in properties, right? A perfect window would have the ability to reflect near-infrared radiation in the summer months, the hot months or hot parts of the world, but let visible light through. But let that near-infrared total transmission through in the winter months when cold parts of the world, so that you can take advantage of solar heat gain. And we need to be able to switch between these different conditions. Also, things like total control of transmission, light scattering, for example. A perfect window can adjust these properties according to the energy efficiency of the building under different solar conditions. So again, a perfect window would have dynamic control over light scattering, dynamic control over shading, light transmission, dynamic control over infrared, near-infrared absorption or reflection, and even maybe dynamic control over thermal conduction itself. So that's a lot to ask for a window. And material science, in the sense of one material or maybe even a combination of materials, can't really achieve all of this, right? These dynamic properties are not currently possible for any one material. Mechanically, of course, we can have dynamic roller blinds, right? Architects have designed moving facades that can control light shading, but this is just changing the total light transmission, right? Here's an example of a smart building facade that changes with humidity to control the shading. And then, of course, we've got electrochromic technologies. This is a very powerful technology that can change, again, the total light transmission using, this electrochemical redox reaction, which is digitally controlled. The trouble is this is not cheap. It's quite expensive, and it's a sophisticated technology, right? So we're changing these optical properties. We see this in airplane windows. So for small scale, high value examples, this can be good, but only really at the moment for total light transmission, right? If we look very, very broadly, there's a lot in this table, but if we look very broadly at all the different technologies that are in development for light control, dynamic light control, to whether it can control total light transmission, near-infrared selective absorption, or light scattering. Not many of these technologies can actually dynamically control these properties, and none of them can control all of these properties, right? That's just beyond what we can do in the field of material science. In biological examples, we can see organisms that can change the optical properties of their skin. The chameleon is a good example, cuttlefish, octopus. These organisms can dynamically change color, light reflection, absorption, using these different layers in their skin that selectively change these optical properties. So these are pigment regions that are expanded in the skin of octopus, for example. And in this organism, this is krill. This is a very small kind of shrimp. It uses injection and flow of pigment within its skin to change its color, change its protection from light intensity by moving pigment around within channels in its skin. So it goes from this transparent state to pigment state. And it's doing this dynamically within a few minutes when it's exposed to too much light intensity. And in general, we see this in arthropods like crabs and other species that can move pigment. For example, in this example here, it's moving pigment around through these small channels to go from a light state to a dark state and so on. So this is actually pigment granule migration through channels. So what we've done is sort of take some of these ideas about biological control over dynamic optical properties and try to apply it for windows. So in these examples, we're taking advantage of confined fluids within materials to change these optical properties. I'll show you a project on pigment injection based on the krill and another project based on multi-layers of fluidic layers that we can relate to this octopus mechanism. So one thing to kind of, appreciate in our approach is the idea of using microfluidic designs where we have small channels embedded into polymer layers, but expanded over large areas. So large XY areas, but thin Z dimensions. So channels expanded over large areas. This is something I started about 10, 12 years ago. I used to work at Harvard University, and this was our project to look at cooling windows. So transparent layers that can have a flow of water mostly and have convective cooling of window surfaces. But what we've done more recently is to look at optical properties, as I said. So based on the idea of the krill, we've been testing out this idea of having an injected pigment fluid injected into a thin layer over large areas. And I'll show you the idea here, but basically we want to use these points of injected pigment within windows as a digitally controlled way to control light intensity. This is our recent paper about this approach. This is what it looks like. Here we see pigment injected through channels within the skin of a fish, tilapia, and this is an example of much larger scale, centimeter scale, injection of pigment within two confined layers. This is called a Healy-Shaw cell. We have a dark pigment fluid that's injected into this host fluid here. And as it's injected into that host fluid, it actually develops these branched patterns, this branched instability. So we got two fluids here, a guest fluid and a host fluid, and they're immiscible. And if we go ahead here, there we go. This is the reason it's branching is because of this instability, this fluid instability called a Safman-Taylor instability, where a guest fluid of low viscosity is being injected into a host fluid of higher viscosity, and it will spontaneously form these branched fingers, and this has been known for some time. What we're doing is using that principle to control the branching of these injected pigment fluids as a function of the flow rate and then as a function of the viscosity ratio between these two fluids. There's the Healy-Shaw cell there, this thin layer. We're injecting this pigment there. So it's a kind of a simple idea, really. We're just injecting a pigment fluid that can then expand and control the light absorption of that layer, just in the control of the radius and the area fraction. And we're using the branching as an analogy to the biological example of these channels that are in the skin of krill. Fortunately, this is also reversible. So as we pull the pigment back, we can go back to the initial state, right? And as we change this viscosity ratio of the two fluids, you can see that the branching is changing in a kind of a predictable degree. And what we've done is sort of match or sort of measure the ratio of these branch fingers and looked at the area fraction of these pigment sites as we inject the fluid. I'll just sort of go quickly here. This is changing the flow rate. You can see how the branching pattern changes quite dramatically as we change the flow rate. And there's examples of that. So as we've looked at the size of the branches, I won't go through this theory about the size of the branches, but it matches the fluidic theory for this instability. But for us, we care about the area fraction. So now we've measured the light intensity in a panel of these pigment points as we inject the pigment. So the light intensity goes down as a function of the area fraction. And what's interesting is we can also have digital control over these pigment injection sites over an array. So here we have light intensity sensors and digital control over the pigment injection, so that as we control the pigment injection over the area, we can have differential response over the shading and the light intensity, and that can be over different parts of the surface. So here we can see a part of the surface that's being exposed to light, and as a result, it injects pigment to reduce the light intensity of that through the window. So it's kind of a smart response to the changing light intensity over this array, right? So this is just a simple feedback system with a microelectronic controller. It's programmed to respond to the light intensity, and as we change the degree of intensity as a gradient across the surface, you can see, just like for the krill, higher light intensity means you have more pigment in that area to reduce the light intensity. So it's a differential response. The amount of pigment is changing depending on the light intensity in that region, right? So, so this is an example of kind of a smart material, smart shading, using this pigment injection. Okay, so it's digitally controlled. And we kind of think there's an interesting analogy to the octopus as well here, because we're changing in the octopus, it's controlling the size of these pigment sacs called chromatophores, analogous to how we're injecting and withdrawing pigment from our points in our surface. We can make this vertical as well. So here's an example of pigment, two fluids that are density matched. So vertically, this pigment spot can increase and then retract over this kind of large area. So an advantage here is that this is just aqueous fluid. It's not expensive, it's safe. And we can use the chemistry of fluids as a way of changing these optical properties. That's kind of the big idea here. So if we go ahead, then I'm just going to skip ahead. Of course, we can use the different sizing of these pig points as a way to control graphical representation in principle, if we were to scale that up, of course. But most importantly, what does this active shading control do for a building? So we've done simulation work here to simulate a three-dimensional space in a city, in this case, Boston, where we know the solar conditions, the seasonal change through the year from January to December. We can measure in simulation the total transmitted solar energy for these different phases of the building. And by changing the solar conditions of these windows in simulation, we can predict the total energy savings and energy required for the building to operate in these environments. And we've compared our sort of fluidic facade to static windows and to roller shades and to electrochromic windows. And what we see, I'll come back to simulate to these energy results later, but what we can see in these simulations of the total energy, comparing electrochromic to roller shade for our fluidic layer, where we have kind of a more dynamic control over the total light intensity, is overall a total energy savings if you were able to optimize the shading at any point in time throughout the year. But I'll come back to this simulation actually later. Instead of liquid fluid, we can inject air. So this is air being injected into a pigment layer, also forming a branched network. And you can see that in this device. This is just a regular, hand scale device. So this is the injection of air into this pigment layer according to this, microcontroller control here. So it's sensing the light intensity change and injecting air into here to change the light intensity. So air has some advantages because we don't have to from anywhere. It's just around the environment of the window. Okay, so that brings me to the second project. I'll try to be not too long here. The second project involves a similar principle of confined fluids within layers, but now multiplying these addition of these layers so that each layer can perform a different optical role. One layer can control the color in the visible range. One can control the absorption, total light absorption as a shading layer. One can be a scattering layer using colloidal particles for light scattering. And one can be a layer for selective infrared absorption, so transparent in the visible, but absorbing in the infrared. In principle, if we stack layers like this, each layer can have an independent control over the total light transmission. That's kind of the idea. So obviously we're just at a prototype scale at this point, but we wanted to test what would happen if we actually generated devices that have this capability. So here's an example of differential color control in the visible by injecting fluids with dye through these different layers at different times. And we can see kind of this, sort of predictable color change as we fill these channels with fluids. Here's an example of the light transmission change as we fill each layer of two layers with this just absorbing fluid, this pigment, to change the total light transmission from obviously from full transmission to full shading here. So as you would expect, the concentration of the fluid or the filling ratio will affect the total light transmission. We've done sort of additive color checking just to make sure that we can have this color control as you would expect. Two layers of different color follow sort of color theory in the additive color. I'll just skip over that. And which is essentially what's happening in the Octop as well. It uses these multiple layers of different pigment types to affect the total effect color of the skin. Maybe more importantly for buildings is light scattering. So if we control the colloidal suspension of the fluid, of course, through the choice of nanoparticles, the refractive index, the size of the particles, we can affect the light scattering, also the concentration of those particles. So here's an example for titanium dioxide. As we change the fluid in the layer to be the scattering layer and change the concentration of that colloidal suspension, we can see the change in total light scattering in the forward direction, or shared between forward and back scattering, or the back scattered, fully back scattered light, right? So it's interesting that you can adjust this scattering behavior of a window through this confined layer of this colloidal suspension. Again, just aqueous, non-toxic chemistry here, but kind of a simple idea, just using the concentration of that fluid to change the light scattering. And this, I think, is really important. Here we have a case of a fluid being introduced into this one layer, transparent in the visible range, but as we inject this fluid into this layer here, you can see that it's absorbing in the near infrared. So here we have a window that's transparent in the visible, but changing its near infrared absorption. And depending what fluid we put through this layer, whether it's air or glycerol or an aqueous suspension with carbon particles, we can see this change in the infrared absorption, and we measured the effective change as a result on the interior temperature of a kind of a model room, as we absorb, we block the infrared. I'm going to skip over this, but this is an example of using the introduction of a fluid into a layer as a way of changing the thermal conduction compared from air to a fluid. So now we've got this independent control over shading, scattering, near infrared absorption, and even light and even heat conduction. Coming back to the simulation results, we've done this energy plus building simulation for this change between total light transmission, near infrared absorption, for example, for this simulated space where we have independent control over these panels on a window. Looking at what does it do for the total energy usage of a building if we could actually optimize the state of this active window at the surface. What does it mean for a building, right? There's a lot of details here. I won't go through this, but we can simulate the solar heat gain, at different points in the year, say for November between these days, using this active switching of near infrared control or active switching of shading control. We can calculate the total energy usage for the building as a result. We've done simulations of the light intensity, the lighting within the room as a function of this shading control, so we can look at the total light. So there's a lighting energy component that we can try to optimize as well. Also based on shading, also based on active scattering of these windows in the simulation. I'm going to skip over this a little bit quickly, but just to kind of make the point that if we have independent control of infrared light transmission, visible light transmission, and scattered light amount, it gives us actually a 3-axis control over total light conditions, right? We haven't scaled up to this point yet, but we're just predicting what a window like this could actually do. A normal modern window is this point here, point in space, because it can't change. The low emissivity coating on a normal window just gives you one condition. A roller shade means you can adjust it along this line, right? The total light transmission along this line. An electrochromic window can adjust along this line. With our sort of 3-layer control, it actually gives us a volume. Any point in this space can be a potential to the point for our kind of 3-layer system. And again, if we consider a simulation space where we could actually optimize at any point in time the light shading, the light scattering, the near infrared absorption over an entire year from January to December, considering sort of the heating energy, the cooling energy, and the lighting energy, we can predict actually the total energy savings for a building if it really could choose the best optimal condition for its facade, right? And what we see is a 43% energy savings compared to an electrochromic window, and about a 60% energy savings compared to just a static window. So there's a huge amount of energy that you can save if you're actually able to control a facade. And I'm going through this kind of quickly, I know, but just to kind of give you this general message here. So other people have also shown that dynamic facades can change the building energy performance a great deal. But this is the results for our particular case where we have 3 independent layers. Okay, so if you think about that number, 43%, ideally predicted over an electrochromic window, and then you think about the total amount of energy that buildings use, it's really a huge energy savings. And so in conclusion, buildings do generally consume the largest fraction of global energy. And we kind of think it's interesting that in the, in our focus on energy savings, we don't normally talk about buildings that much. We sort of focus our attention on transportation or green energy, energy storage, which makes sense. But we should also be talking about buildings in the biggest fraction. So that we think there's a significant need for dynamic building facades with active control over these optical properties, shading, near-infrared light absorption, and scattering. Solid state materials can't get us there, at least at the moment, right? So we have to think of alternative technologies, and that's why we're thinking about these sort of low-cost fluidic networks that use confined fluids and the chemistry, huge range of chemistries that we can use in these different confined fluids as a potential way to have this kind of dynamic control. So we've done this simulation and these prototypes for active shading to try and see what it could do. So I want to acknowledge the work of Raphael Kay, the student who did this work, our collaborator in architecture, Alston, funding sources, and I am happy to field any questions that you might have.
We have a question from Dr. Hisham Saad. He says, do the using of AC, which depend on solar energy, make a difference?
Oh, that's a good point. Yeah, I mean, if you could use an energy source that's not generating carbon, then you sort of have a carbon neutral situation. But air conditioning, I guess our point is that air conditioning, if you can reduce the total need for air conditioning, right, it really helps many indirect and direct benefits of that, right? So a smart building facade can, I think, significantly reduce the need for air conditioning. I mean, air conditioning, yeah, if you could have a green energy source, that's good, but you're still also dumping that hot air out, right? So air conditioning is kind of problematic in urban environments because it makes the outside regions hotter and it's sort of worse for everybody, right? So I think if we can totally reduce the need for air conditioning, it helps generally. Any questions?
Thank you very much, Dr. Hatton, for this great session.